Okay, and what you see here is the final look of the previous study when we solved a one-dimensional stationary heat conduction problem on the interval 0 up to 1 here, with the boundary conditions that the temperature was 0 at x equals 0, temperature, and at x equals 1 we had a thermal isolation condition. So now no heat is leaking out here. Inside the interval we had a uniform heat production of intensity 2, and all material properties like heat conduction and density and heat capacity and so on was set to 1 for simplicity. What we shall do now is to try to turn this into a time-dependent problem, a time-dependent study. What I've done further here is to solve or to save this work, this study, with a name. So I did that. I saved it with the name example1, and the way I did this is to go to the file menu and simply use the save as and give it a name. So that is already done here. Now, how do I now make a time-dependent study out of this? Well, I do exactly as I said. I go here to this project, and I right-click this one, and I add a study, a new study of more or less the same physics. And now I here make the choice a time-dependent study. Before we pick this one, the stationary. Now I left-click time-dependent here to make my choice, and I go to the finish flag. Okay, so now some choices have to be made. First of all, this is the time range on my study. It starts at the time 0 and it ends at time 1. And I go by steps 0.1 from 0 to 1. Now this 0.1 here, this is how frequently I save the solution for later presentation to have a look at. So it doesn't have anything to do with the actual time steps taken by the solver. We shall come back to that later. But this is how frequently you save the solution. So the solution is saved and stored for time 0 and up to time 1 second. And every 10th of a second the solution is saved. I could change this, of course, but this is good for now. What I have to do further is to specify the initial temperature. And this is over here. Initial values, it was there from the beginning, but it didn't have any meaning when we had the stationary problem in mind. So I left-click this one, and I can then, in my domain here, pick an initial temperature distribution. So in this case I start with a 0 temperature. I could start with something else also, but let's just have it like that. So t equals 0 here is the default choice that was there from the beginning. So now everything is set for this problem. The material properties is the same as before. The heat production, I don't change that, it's the same as before, uniformly 2. And I now go here to my study 2, the time-dependent problem. I right-click this one and I pick compute. And after a few seconds I get the solution presented to me here. So what you see down here, the blue line, this is the initial temperature distribution, that was 0. And up here, the green curve is the temperature at time 0.1. And the red one is the temperature at time 0.2, and so on. And this is then the temperature after 1 second. And what you see here is that the temperature goes up because of the heat production we see that we keep the temperature 0 to the left, and we keep isolation to the right here. The temperature derivative is 0, indicating no heat flux. You also see that the temperature distribution seems to converge here to a certain state. It sort of doesn't grow much more, and what happens is that we here sort of reach more or less or converge to the stationary state. And that was the thing that we computed in our first study. So the solutions here, the solution curves approach what was the solution to our previous problem with solution 2x minus x squared, if I remember it right. Okay, so once you have the data for the stationary problem introduced, you can easily go to make a time-dependent study in this fashion. And that